Vesper theory. So this is a theory, which in science means explanation, about how the valence shells electrons around an atom, the pairs of those repel each other and give a molecule a particular shape. So recall that covalent bonds occur when electrons are shared between two atoms. So we're talking about the bonds within a molecule. Valence refers to the electrons within the outermost orbit. We're going to ignore all the electrons around the atoms except for those valence electrons. And we have to be able to draw Lewis structures so we know what the bonding is going to look like within the molecule, and then we can apply our Vesper shape to it. Vesper theory describes the geometry of atoms. In order to minimize energy, those atoms are going to arrange themselves in a particular way, and that's what Vesper is all about, is figuring out that particular way, those shapes. Vesper theory is going to indicate the polarity of the molecule, because once we know how the atoms are arranged, we can figure out what sort of difference in electronegativity they have, and therefore be able to predict the polarity of a molecule as well. Essentially, electron pairs that are around atoms, whether they're bonded or not, are going to repel each other, and this is going to give them their particular shape. Lone pairs are more repulsive than bonded pairs, so they're going to spread out they're going to require more space than bonded pairs, but even bonded pairs aren't going to want to be that close together. So we're going to use Vesper notation, and essentially this allows us to generalize a particular shape, which could apply to multiple different molecules. We're going to use A for the central atom, and generally we'll start off by sticking to relatively small molecules with only one central atom. Atoms around it, or you can think of the atoms that it's going to be bonded to, so bonded pairs, we're going to use an X for, and then any lone pairs that has, we're going to use an E for. So you have to be able to draw the Lewis structures in order to figure out how the atoms are arranged without particularly paying attention to the shape. And then the Vesper will allow us, or applying the Vesper rules will allow us to come up with a specific shape for that molecule. And one thing to note is that double and triple bonds are always going to be treated as if they are a single bond. So whether they are a double or triple bond based on our Lewis structures, we don't care. We're just going to see them as being a bond, because if you think, if you had an atom bonded to another atom, whether it was a single bond or if those two atoms were bonded with a double or a triple bond, their relative position is going to be the same. So we're going to go through these 5 different aspects of several different examples. We're going to look at the valence pairs, so the total number of bonded pairs and lone pairs. We'll specify whether it's a bonded or a lone pair around those atoms and how many. We're going to use the Vesper notation using those letters, the A, the X, and the E. We're going to go over the names of those particular shapes, and then we're going to draw a diagram and look at an example molecule for each one as well. So the first one, most easy one, linear. If you have a central atom bonded to 2 other peripheral atoms, and when we have more than one, we use subscripts, just like with the chemical nomenclature. So in this, there's a total number of pairs of any sort of 2, of which both of them are bonded pairs. So there's only 2 bonded pairs. There is no lone pairs on that central atom. This is going to create a linear shape to it. Those 2 bonded pairs are going to be as far apart as possible. So an example of this, we built it with a ball and stick model. We have a central atom, so that is our A, and we have our, let's see if we can, there we go, and kind of see that, A, and then we have our peripheral models, which we're just going to label X. So they are going to be bonded to each other. We don't care if those are double bonds, triple bonds, single bonds. It's all going to have the same shape. And we're going to end up with this linear shape. Now, obviously, if it's a line, the angle between those 2 is going to be 180 degrees because it's a straight line. So an example of this would be carbon dioxide. And again, notice the double bond. We don't care. We're treating double bonds, triple bonds, single bonds all the same because they have no effect on the shape. Vesper ignores them. They're there, we just don't change the shape of them. So carbon dioxide would be an example of a molecule with a linear shape. We would use the Vesper notation of AX2 to denote the Vesper notation for something like carbon dioxide. Again, the central one represents the A, the X's are bonded to the A on the outside, and anytime we have a central atom bonded to two peripheral atoms, this is going to be the shape, as long as that central atom does not have any lone pairs. If it did, it would have a different shape. All right, looking at this particular shape. 3 pairs of electrons around the central atom, and they are all bonded pairs. Again, no lone pairs yet. So 1 central atom, 3 peripheral atoms. The name for this is trigonal planar. So easy to remember, trigonal, there's 3 peripheral atoms around it. Planar should tell you something about the shape of it as well. Remember, these are 3-dimensional. So again, if you had a, can't see very well in the middle here, A, and then if these are X's on the outside, X, 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 there's 3 of them on there, and so this is going to be the shape. Now these guys are going to want to try to spread out as far away from each other as possible, so that's the repulsion part. They're all going to want to be equally distant from each other, and so you can imagine we have a circle here and we have 3 spokes to it, so they are going to want to be as far apart as possible. So that should help you remember the bond angle for these ones. A circle is 360 degrees, so if you divide that into 3, you're going to get a bond angle of 120 for each of these. 120 and 120 will be the bond angle for this particular shape. And notice it all fits on one plane here. There's none of them sticking up out of the plane, either up or down. They're all on the same plane, hence the name planar. So an example for this would be, say, if you have boron bonded to 3 fluorines. Boron does not have any lone pairs, so it is just A with 3 peripheral atoms around it, AX3. It's flat, so it's planar. 3 things around it, trigonal. And again, remember, you've got your 360-degree circle divided by 3 is going to tell you the bond angle between these is 120. All right, angular bent, also sometimes called V-shaped. It's an S. V-shaped. So if you take our AX2 that we saw earlier, but now you add an E, and remember that means that you have a lone pair of electrons that is on the central atom. So these all kind of refer to what's happening around the central atom. It's saying that there's 3 things around the central atom, 2 of them are bonded pairs, 1 of them is lone pair. So there's our central atom, there's our 2 bonded pairs, and there's our 1 lone pair. And this we can call angular, V-shaped, bent, any of those are good. So here is a picture denoting the lone pair here. So think of that as a pair of electrons. If you're drawing your Lewis structure and you get a pair of electrons, and you have your 2 peripheral atoms, they're going to be bonded to your central atom, A. Now, this lone pair is going to push on those bonded pairs, so it's no longer going to be a 180 degrees. They're going to be getting closer together, and so this is going to be less than 180, and it tends to be somewhere around 120. These aren't exact angles because it does depend on which atoms are around it, but it tends to be somewhere around 120 for an angular shape. So an example of this would be SO2. We've got a lone pair on there. That is the E. We've got these 2 peripheral atoms, which are the X's, and then our central atom, which is the A. And remember, our double bond might as well be a single bond because they look the same in terms of Vesper. It is there. We draw it in our Lewis structure, just Vesper ignores it, and we end up with about a 120-degree angle. Tetrahedral, really important one. Here is a central atom with no lone pairs, and instead it has 4 bonded pairs. So they're all bonded pairs, and the name for this is tetrahedral. We'll see this shape a lot. If you think about it, octet rule, tetrahedral being very common, should make sense. We have our central atom here and our peripheral atoms around it, and they're going to set up in this tetrahedral shape. This is the best way to spread out if you have 3 dimensions to work in. So if you think about it, we've got, it's no longer just a circle that's being divided by 4, which would give you 90 degrees, because that's limiting you to one plane. Since we have 3 dimensions to work with, we've got a whole sphere that we can divide evenly into 4 different parts. And that's going to give us our bond angle for our tetrahedral molecules like methane here. So it turns out when you take a sphere and you divide it evenly in 3 dimensions, you're able to get these sort of cuts, you could think of it as, or these bonds spread out, and the angle between them ends up being 109.5 degrees between each of these bonds. So all of them are going to be 109.5. And since when we're drawing it on a 2-dimensional shape, it's sort of hard to show that one is sticking into the page and what's sticking out. So we kind of use these type of bonds here, and we say, okay, if I want to show that there's carbon, I can put, let's do that in black, carbon, I can put 2 of these on a 2-dimensional sheet and get the bond angle of 109.5 degrees. But if I go to put another one on, I can't get that 109.5 degrees on 2 dimensions. So I would have to actually make it stick out of the paper. So this hydrogen here would be sticking out of my sheet, and I need to do another one in the back there that is sticking into my sheet. And so that's the idea behind trying to draw it like this. We're using one dashed triangle to represent the bond that's pointing into the sheet, and one solid triangle to show the bond that's sticking out of the sheet, just as a kind of non-artistic way of trying to draw it looking 3-dimensional. All right, trigonal planar. So this one here, we have 4 bonded pairs, but 4 Vesper pairs, 4 valence pairs. 3 are bonded and 1 is lone. So we end up with AX3 with 1E. And this one forms a trigonal pyramidal. Just remember, we only have 3 bonds to work with. It's not going to be planar anymore, so it's not trigonal planar because of the lone pair. The lone pair is going to force those other bonds to get closer together than they would have been in our trigonal planar. So imagine we have our peripheral atoms here, our central atom, and our lone pair up top. So that lone pair is going to push down on these guys and make them bend downward. They won't be able to sit flat because they want to, this bonded pair wants to get away from this lone pair up top. So this will end up pushing them a little bit close together, and they end up with a 107 degree angle between their bonds because, again, that lone pair pushes down at them. So it's not 120 like it was with trigonal planar. It's also not on a one single plane because they're being pushed downward. So think of this as it's kind of like a pyramid, 3-sided pyramid. So trigonal pyramidal should stick in your head, and 107 happens to be the angle there. Again, if we're trying to show this 3-dimensionally, we can put one of them on our page, that's fine, but then since it's a pyramid, one of them is going to stick out from the page towards us, and one of the hydrogens, or whatever it happens to be, that other atom, is going to stick into the page away from us. And I like to put the lone pair on there as well, just so I remember that it's there. But there's an attempt at drawing a 3-dimensional looking structure without having to get out our sketchbook and make it look too artistic. All right, angular bent again. So this is another type of angular bent one, but it has with it 2 bonded pairs and this time 2 lone pairs. And this is another popular one just because of a particular molecule that we all know and love has this particular shape to it. So it wouldn't be linear. So you can imagine, remember the linear one was like this and it had a 180 degree angle. But if you put a lone pair, it's going to push those guys together. And if you put 2 lone pairs, it's going to really push those guys together. So these guys end up being bent towards each other, and more so when we had, let me move this guy over a little bit. When we have 2 lone pairs, the angle between them actually ends up being quite a bit smaller. It's not 180, it's not 120, it actually ends up being 104.5. So this one here is our common example for having that angle, which is even less than before. So let's go through our examples here. So when we looked at our linear one, AX2, we knew the angle was going to be 180 because it's a straight line, degrees. If we had A with a lone pair, X2, it brought that angle down to a smaller let's get this in green, 120 degrees. And this one here, we have two lone pairs. They're going to take up even more room. So the peripheral atoms get bent even closer together, and we end up with an angle of 104.5 degrees. So think of that lone pair. If it's not there, the atoms are able to spread out and have a nice linear shape to it with a 180 angle. If there is a lone pair, they get bent closer together. And if there's two lone pairs, they get bent even closer together. So it goes from 180 to 120 to 104.5. And then there are a couple other more unusual ones you won't see too often, but it's a good idea to see several of them. We'll go over two of them just because they're kind of interesting. We'll talk about them more when we do some bonding. So trigonal bipyramidal. So this one here has two pyramid shapes to it, and they happen to be three-sided pyramids. So imagine two three-sided pyramids. That's kind of how you can imagine this one. They're all bonded pairs. We have a central atom with 5 bonded pairs around it. So there's an example of what the model might look like. And phosphorus pentachloride would have this particular shape to it. And so you can imagine that we could probably get 3 of them to be on a plane. So there's different ways to look at it, but you can imagine you had phosphorus and you could fit 3 of these guys on a plane like so. So these are chlorines. If it was just those 3, they would all fit on one sheet of paper. But there's another 2, so you have to imagine they're kind of sticking up and down right through the paper. So it's almost as if we have a trigonal planar shape with these other guys sticking right through the center here. And so if you think about the angles, we would have between the trigonal planar, just like with trigonal planar, we know that's 120 degrees. But then right here is a 90-degree right angle. So we can sort of think of these as two shapes. And there's another 90-degree right angle, and then there's another one right there coming straight at us. So I think of this as being trigonal planar. If you imagine the phosphorus in the middle, a chlorine up top, and a chlorine on the bottom, and then 3 chlorines on this plane right here in a trigonal planar shape. So we end up with a 90-degree right here, and the plane right here has 3 chlorines on it, each with a 120-degree angle to it. Then there is octahedral. There's 6 bonded pairs around it, which begs the question as to why is it called octahedral, because you know what that prefix stands for. And so this one here has one plane running up like this. You can imagine we have our 2 peripheral atoms, one up top, one at the bottom, and then all on the same plane we have our other 4 peripheral atoms. And since there's 4 on a peripheral plane, these guys here have a 90-degree angle to them. And then these other ones up top have a 90-degree angle relative to the plane of the 4. So think of sulfur hexafluoride, 6 fluorines around it. And you can sort of think of these guys as all being on one plane. So that's on the XY plane. And you can think of these guys being on the other plane. So if you think of a 3-dimensional Cartesian grid, you've done 2-dimensional before. So we have our X and our Y. And then if you did a Z plane on there as well, stick an atom on each end of one of those planes, you have an octahedral structure. The reason why it's 90-degree angles, as we see with a Cartesian grid. Octahedral because it doesn't have 8 bonds on it, but it does, if you were to imagine it as a three-dimensional shape, it would create 8 surfaces. And so that's where that name octahedral is coming from. Lots of other ones out there. For more exotic ones, you start doing weird things with the noble gases with lots of lone pairs, you can get some other shapes, but those are the main Vesper shapes that you should know.